Hello friends, welcome to NPTEL online certification course on soil and water conservation engineering. I am Rajendra Singh, professor in agricultural and food engineering department of IIT Kharagpur. We are in week number 3, lecture 15, and today we will be solving problems on graded bunds. We saw the principles of and components of graded bunds in the previous lecture. Today we will utilize them to solve problems on graded bunds. Just to give you an idea of the course content which we have gone through in this particular week, we started this week with lecture 11 where we introduced bunds. Then in lecture 12 we went through contour bunds, that is design parameters, design principles, design considerations. And lecture 13 we applied those design parameters considerations into solving some of the problems dealing with the design of contour bunds. In previous lecture, that is lecture 14, we covered graded bunds, and today we will be solving problems on graded bunds. Let us start with problem number 1, which reads: a 350 meter long graded bund has been proposed to be constructed on a land of 3% slope. So, length of the graded bund is given as 300 meters and land slope is given as 3%. The type of soil is sandy. So, soil we are dealing with is sandy soil. The rainfall intensity of the area was recorded as 18 centimeters per hour for the duration equal to time of concentration. This is very important. The duration of the rainfall is also given, that is rainfall intensity is given as 18 centimeter per hour, but important thing is the rainfall was for duration equal to time of concentration. And we have to maintain a uniform grade of 0.18% along the bund. So, this is also, so it is a graded bund. So, that is why a uniform grade of 0.18% has to be maintained. Further, its problem says that assume Vi, that is vertical interval, is 1.25 meters and runoff coefficient C is 0.35. Using the above data, determine the dimensions of the bund. So, we have to determine the dimensions of bund, and dimensions of bund we saw that simply means we have to design or decide on the top width, the bottom width, height, side slope of the bund. So, this is typically this is how a cross section of a bund looks like. So, what we have to decide on this side slope, and then we have to find out what is the bed width or bottom width, what is the top width, and of course, the height. So, this is what problem wants one to design utilizing the data that is given. So, let us see how to go ahead with this. Now, just to have a check on the data which is available with us. Length of the bund is given as 350 meters, land slope is given as 3%, rainfall intensity for duration equal to time of concentration is given as 18 centimeter per hour, the grade of the bund is given as 0.18%, vertical interval is 1.25 meters and runoff coefficient C is 0.35. Now, in any of such problems we have to decide on the dimensions of the bund. So, the determining factor of course is the amount of water, the flow that the structure has to handle. In this case it is a graded bund. So, we remember that graded bunds are designed for safe removal of excess flow. So, that means whatever flow is generated over the area between these two bunds, we have to design in such a way that the dimensions and all, so that it is taken off safely from the area. So, that is why the computation of peak runoff rate becomes the most vital thing. This is the first thing. And just to give you an idea, I mean or just to remind you that we discussed how to determine the peak runoff rate, and we also decided that we read that for determining the peak runoff rate from any area watershed catchment, we use rational method. which I also mentioned that you should always remember, because this is such a fundamental thing, and this is given as CIA by 36. This is the formula. And also remember, when we discussed this formula, we also said that there are certain units which we should always remember. So, in this case Q is in cubic meter per second, C is the runoff coefficient, which is a coefficient, the value is given here is 0.35, I is rainfall intensity, for duration equal to time of concentration, exactly the data which is already given. So, we have been given rainfall intensity already in the problem, and the unit here is centimeter per hour, and A is the drainage area, and the unit here used is hectares. So, that means we need to know for this CIA, and in this problem C is already given, I is already given. So, we have to find out A, that is the drainage area, and obviously because we are talking about the graded bunds. So, the area lying between two consecutive bunds, that is the drainage area we are talking about in this case. So, we have to find that out. So, let us see how to do that. So, for doing that, the first thing we need to remember or determine is the horizontal spacing of bund, because you remember we said that if this is what we are talking about, this is one graded bund, this is another graded bund. So, this is the area we are talking about, the area between these two we are talking about. So, in this case obviously we decided that there is something called horizontal interval. So, this is horizontal interval, any corresponding point we can take in two bunds, and the horizontal distance between that is horizontal interval. So, that horizontal interval basically, and the length of the bund, length which is the perpendicular to the board basically. So, this is what the area we are looking for, that is the area in which whatever rainfall occurs, that we have to handle. So, that is why that becomes the drainage area, or that will decide the peak runoff rate which we have to handle. So, that is why the first thing we need to determine is horizontal interval, and we know that from previous class also, and also in contour bunds we know that there is a direct relationship between horizontal interval and vertical interval, that is HI equal to VI by S into 100, and I also said that you do not have to remember this formula, because this is vertical interval, this is horizontal interval, and at the same time we also know that it is S by 100. So, this land slope is S percent. So, S by 100, generally we take it S is we designate S for land slope. So, that simply means by equivalent triangle we can write that S by VI equals to 100 by HI, or HI is equal to 100 VI by S. So, that is the formula here, 100 VI by S. So, as I also said in the previous class, you really do not need to remember all the formulae all the time, you can many times you can derive the formulae. So, in this case for us vertical interval is already given, land slope is already given as 3%, that is here. So, data both the unknowns are given here. So, putting the value of V I and S, if you calculate that, we find that H I is equal to 41.66 meters, or approximately 42 meters. So, area formed between two consecutive bunds, already we have explained that it is H I times length of the bund. So, H I is we have calculated, length of bund is already given. So, this is in meter, this is in meter, total area in square meter. So, that comes out to be 14,700 square meter. But remember in CIA the unit required is hectares, and that is why we have to divide this by 10,000 square meters, that is 10,000 square meters equal to 1 hectare, you remember. So, by doing that we get the area is 1.47 hectares, that is the drainage area. And once drainage area is known, then we can put the values in Q equals to CIA by 36. So, C is known 0.35, I is given as 18 centimeter per hour, the drainage area we have already calculated is 1.47 hectares by 36. So, the value of Q comes out to be 0.26 cubic meter per second, and that is the discharge our system has to, our graded Bund system has to handle. So, this is important finding for us. Now, let us come to, now we know what is the discharge that our system has to handle. So, now we can go ahead and decide on the components of the graded Bund or the cross section basically. So, first thing we decide is the side slope of the Bund, and that we have already seen that is a function of type of soil, and because the soil is given as sandy. So, the side slope of the Bund will be 1.5:1. So, this is already a standard value. So, we are taking that as 1.5:1. Now, this comes the definition sketch. So, this is typically we say is D or H, that is depth of impounding, and this land slope is 3%. Now, what we are doing here, we can calculate the values, but what we are doing here, that is this is one of the alterations that you can also assume the value and go forward and calculate. So, what we are doing here, that we are assuming that the depth of water H is 0.3 meters. So, this is our assumption. Instead of calculating the value, what we are doing, we are starting with an assumption, which we can always do. So, we are, once we assume this as 0.3, this slope we already know is 1.5:1. So, that means if this is 0.3, this is H, this distance is 1.5 H or 1.5 times or 0.3, that is how we are getting 0.43 meters, and this is 3% slope. So, this is 3%, this is 0.3. So, obviously, if we calculate this will come out to be 10 meters. So, that is why AD is 10 meters and DC is 0.45 meters. And then again this is sandy soil. So, again this is a seepage line, and the slope is being taken as 5:1 because it is a sandy soil. So, this all these components all these parameters, design parameters are here in front of us, and then we have to decide on the total height and the base width and the top width, and then we have to see that it should be able to handle the discharge for which it is being designed. So, now basically the total area will be area of triangle ABC, that is area of ADB and area of BDC. Let me just go back to the previous equation. So, basically what we are saying is that this is the total storage area. So, it is sum of two triangles, that is total area is sum of area ADC plus area BDC. This is 1 and this is 2, 1 and 2. This is 1 or 2 triangles are there, and we have all the values here. So, we know that ADC is half times, this will be ADC will be half into 0.3 into 10, and BDC will be half into 0.3 into 0.45. So, this is how the values will come. So, that is what we are doing here, that is 10 meters. A1 we are calculating half into 0.3 into 10, 1.53 square meters, and second triangle BDC A2, which is half into 0.3 into 0.45, that comes out to be 0.0675 square meters. So, total area of ABC is A1 plus A2 comes out to be 1.57 square meters. So, this is the total area which we have, which should that we storage area basically what we are talking about. Now, next thing we have to calculate is wetted perimeters. Wetted perimeter we saw that it is nothing but the length that is in constant touch with water. In this case, it will be AB and BC. So, AB and BC we can again same triangle, two triangles are there. So, we can find out AB square is equals to BD square plus AD square, that is 10 square plus 0.3 square, this is here, and this BC square equals to BD square plus DC square, that is 0.3 square plus 0.45 square, and square root is being taken. So, on solving we get a 10.54, that is weighted perimeter is 10.54. So, hydraulic radius is A by P, A we have calculated, P we have calculated, that comes out to be 0.15 meters. And then obviously, for flow velocity we have to use the Manning's formula, which is 1 by n r to power 2 by 3 s to the power half. So, 1 by n value we normally assume as 0.05. So, that is what it is being assumed, and this is 0.15, and the grade of the channel is given 0.018. So, in percent we are writing here 0.018%, same, and then we are calculating the value of velocity, which is 0.3 meter per second we are getting. And you remember, non-erosive velocity means it should be less than 0.5 for sand and 0.65 in any case. So, this is here, this velocity is non-erosive. So, that means from knowing the velocity and area, we can calculate Q, which is here. The channel capacity obtained 0.437 is greater than the required. We require only this much and we are getting much greater. So, we may accept this, or we may go and reduce the value of depth of ponding H. So, that is what I mean, if you assume the value, you have to iterate it. So, that iteration process is there, but we are not doing, but because you can do that anyway. And once H is calculated, then the base width will be Ns plus Z times H, that is 5 H plus 1.5 H, many times you have done that. So, it will comes out to be 1.95 meters, and the top width will be the total height of the bund will be depth of water plus freeboard. Generally, we are assuming 25%, but let us say we are assuming here is 15 centimeters. So, the total height comes out to be a 0.45. So, the top width will be base width minus 2 times of top total height times 1.5, which is the side slope. So, that comes out to be 0.65. So, this way the different dimensions of the bund we obtained are, the height is 0.45 meters, base width is 1.95 meters, top width is 0.6 meters, and side slope, that is soil dependent, which we started with is 1.5:1. So, this is how we have designed or handled a particular problem. Let us take the next problem. Determine the dimensions of a graded bund which has to be constructed on a land having a slope of 2% and vertical interval of 1 meter. Soil type is sandy. So, a side slope of 2:1 is recommended, and the slope of the seepage line is 5:1. So, these slopes are already given. The channel formed between the bunds is under vegetation with Manning's roughness coefficient value of 0.04, and it has a bed slope of 0.25%. The graded bunds are to be constructed to drain a flow of 3.5 cubic meter per second. So, in this case flow is already given. So, we have to determine the dimensions of the bund and also calculate the volume of earthwork per hectare, assume a freeboard of 15 centimeters. So, almost all data is already given, including the flow in this case. So, in this case we can straight away try to use the height of the bund formula, which we saw we almost derived using this research paper. So, which is where H is a function of Q, N, Z and two slopes, capital S and small s. Remember, capital S is the channel bed slope, and S is the land slope. So, all the values are given. Q equals given as 3.5 cubic meter per second, N is given as 0.04, Z is 2, S is 2%, capital S is 0.25%. So, all the unknown values are given. So, putting these in equation, we can solve H and solve for H, and that comes out to be, the value comes out to be 0.62 meters. So, H comes out to be 0.62 meters. And once h is known, then obviously we have to get the gross height of the bund. The freeboard value is given is 15 centimeters. So, the gross height of the bund is calculated height plus 15 centimeter, that is 77 centimeter, or 0.77 meters, that is the value of h we have obtained. And once h is known, the rest of the things are simple. We know that bed width is depends on ns plus z equal to into times h. Ns is given as 5:1, that is the seepage line slope. Z is given as 2:1, that is z is equal to 2. H we have already calculated 62, so that comes out to be 4.34 meters. Top width is b minus 2 times z and capital H, that is the gross height. So, 434 minus 2 into 77, that is the gross height, or it is 1.26 meters. So, because in this problem everything else was given, we straight away calculated the value of h, and thus it was simpler to calculate all other values. So, now we have to, in the second part of this is we have to calculate the earthwork, and for earthwork per hectare we required horizontal interval, and we already know the relationship between horizontal interval and vertical interval. The value of vertical interval is given. So, horizontal interval comes out to be 50 meters. So, length of graded bund per hectare is 10,000 square meters divided by hi in meters, that is around 200 meters horizontal interval, and the volume of earthwork per hectare is cross section times length. So, cross section of the bund times the length per hectare, and cross section is function of T, B and H, and T, B and H all we have determined. So, it is 0.5 times T, B, H, all the values we have obtained. L also we have calculated. So, work comes out to be 431 cubic meter per second. So, that is pretty straightforward. It was simple because values were all given to us. So, the final answers are dimensions of the mother, height equals to 0.77 meters, base width 4.34 meters, top width 1.26 meters, side slope 2:1, and volume of earthwork per hectare 431 cubic meters. So, this is what the answer will be. Take the third problem. In a given area having land slope of 2%, graded bunds have to be constructed with channel between them to drain a discharge of 0.005 cubic meter per second. The bund should have side slope of 2:1 according to recommendation. The runoff depth of the field was calculated using Nrcs curve number technique considering AMC2 condition, and curve number for the area was reported to be 75. This runoff depth was considered to be the depth of ponding behind the bund. Using the above data, what channel slope can be recommended between the bunds? Use n equals to 0.04 and 6-hour rainfall, 24-hour frequency rainfall is 120 millimeters. So, in this case we have been lot of data is given, but important thing is that we have to calculate the runoff volume in depth terms using Nrcs curve number technique. So, that is important. And if you remember, the Nrcs curve number method is used for calculating the volume of runoff in depth units, and this is how the curve number formula looks like. Vq equals to P, which is precipitation, S, which is potential maximum runoff, and P minus 0.2 S square by P plus 0.8 S, and S is related to curve number by this formula. S is equal to 25,400 by curve number minus 254. This is when S is in millimeters, this particular formula is used, and because curve number is given, by putting curve number here we can get the maximum potential retention. S value is 84.67 millimeters, and for this area the precipitation value is also given to us, that is precipitation is given as 120 millimeters or 12 centimeter, and value of S we have calculated is 8.467 centimeters. We are converting into centimeter because the value of P and S required for in the curve number method are in centimeters. So, now putting these values in desired units in this formula, we get Vq equals to 5.66 centimeters, and H per problem definition, this is the depth of ponding. So, depth of ponding previous cases we calculated, in this case calculating Vq we directly get the depth of ponding. So, this is another variation of the problem which we might face. And once we have obtained this, once we have obtained, we can substitute all the values, because q is known, n is known, z is known, s is known, and h is known. We can substitute in this. So, only unknown is capital S or channel bed slope. So, by putting all the values in this equation and solving, we get S equal to, or the channel slope equal to 0.0674%. That is, the recommended channel slope is 0.0674%. That is what we have to calculate, we had to calculate in this particular problem. So, now we go to the last problem. Design a 300 meter long graded bund for cultivated land with sandy soil, sandy loam soil, surface slope of 4%. Bund channel is to be formed by embankment only. The horizontal distance between two bunds is 50 meters. The maximum depth of rainfall in the catchment with 10-year return period is given below. So, duration versus depth of rainfall relationship is given here. So, data available are length of bund 350 meters, land slope 4%, soil sandy loam, HI 50 meters, and rainfall data is given. So, obviously, here again we have to determine the peak rate of runoff using rational method. In the previous case which we handled rational method, there we had been given rainfall for time of concentration, for duration equal to time of concentration, but this is not the case. So, here we have to calculate the time of concentration Tc using Kirchhoff's formula, which is Tc equals to 0.0195 L to the power 0.77 S to the power minus 385, and the total length which the flow has to flow path length which we consider is horizontal interval plus length L, which is the length of the bund itself, the perpendicular distance we always talk about. So, because if we consider here in 3 dimension, if you see here, so that means any drop which occurs, first it has to flow here, that is horizontal interval, and then the length. So, that is the maximum length which comes out to be 400 meters in this case. And total elevation drop will be, plot width is 4% slope over 50 meter is 2 meters. The total length of bund is 350 meters. So, what we are doing as a variation, we can say that we are breaking that into 4 different parts, 5 meter, 75 meter, 100 meter, 100 meter, and we are saying that the variable slope is provided. So, the lower 75 has 0.14%, the second 75 is 0.13, drop 100 meter is 20, and upper one has 0.1%. So, for each we can calculate the slope value, because length is known, slope percent is known. So, slope length we can find out, and thus the over the channel the total drop which comes out to be 0.4225 meters, and the total drop comes out to be 2 plus this, that is 2.4225 meters, and that means the total slope will be h by L, that is total drop by over length. This is drop, this is length 0.06. So, in formula now we know L, we know S. So, by putting this formula we get a value of 14.07 minutes, and then we have to use this for obtaining the data from the table itself. So, if you look at the table, the value is given for 10 and 20, we have to obtain for 14. So, obviously, we can always interpolate in between these two. So, interpolating we get 25 plus 55 minus 25 by 10 times 4. So, total it comes out to be 37 millimeters. So, rainfall intensity for 14 minutes, that is rainfall in 14 minutes is 37 millimeters. So, the intensity will be 37 by 14 into 60, that is 158.6 millimeter per hour, or roughly say 16 centimeter per hour. So, once Tc is known, we can the intensity is known, we know the C, we know the total area, because H, I and L are known. So, area is known. So, we can put in rational formula to get the value of Q p, which comes out to be 0.23 cubic meter per second. So, that means we have to handle this discharge, and then rest of the things, side slope for sandy loam is known 1.5:1, for seepage line for sandy loam is 5:1. We assume a depth of 25 centimeters, and like previously we have solved this problem, we can go ahead and get the cross section, etc. So, here the sum of two areas we will find out, which comes out to be 0.83. We calculate the weighted perimeter, and once we have done that, we calculate the hydraulic radius, which comes out to be 0.1234 meters, and once hydraulic radius is known, then we can use the values in Manning's equation to calculate the velocity of flow, which comes out to be 0.23 meters per second, which is non-erosive. So, no problem, and discharge capacity Q equals to A V comes out to be 0.1319 cubic meter per second. The problem is that channel capacity we are calculating 0.13, but discharge we have to handle is 0.3 cubic meter per second. That means the channel does not have sufficient capacity to carry Q p. So, we need to increase D and recalculate the dimensions. So, this is the variation, because this calculated value is not sufficient to handle the desired discharge. So, obviously, then it is just a iteration. So, we will go and change the value, calculate A, calculate P, then calculate hydraulic radius, which new value comes out to be 0.14147, and then we have to now calculate once again the velocity, which is 0.54, is fine, still fine, and then Q value we have to calculate, which comes out to be 0.64 square cubic meter per second, which is sufficient because the discharge we had to handle was 0.23. So, channel now has sufficient capacity to carry Q p under non-erosive limits. So, that means we have handled the problem. So, the Bund dimensions, the discharge is handled. So, the Bund dimensions can be calculated. The base width of Bund we know how to calculate, height of the Bund we know how to calculate, then top width of Bund we know how to calculate. So, once h is known, everything else can be calculated easily. So, thus in this case the final answers are height of the Bund 0.45 meters, base width 1.95, top width 0.6, side slope 1.5:1, discharge capacity is 0.64 cubic meter per second, which is slightly higher, but we accept that. So, with this we have handled 4 different kinds of problems, and where ultimately we have to have flow with us, and once flow is there, that for estimating that flow we might have to use rational method. We might have to find out the time of concentration if required, and also it is possible to use the SCS curve number technique. So, all these will be used for finding out the flow. Once flow is known, then we can either assume the value of D or go and calculate the value of D, and then other dimensions. So, if you practice few more problems like this, and we will be putting some problems into assignment, I think things will be very clear to you. Thank you very much.